So in the previous lecture, we looked at the paramagnetic state. So this is where we had atoms with individual magnetic moments, and those could be completely isolated, in which case we have the sort of Curie paramagnetism. And then potentially in a solid, we may have the situation where there's interaction between these magnetic moments, and that interaction leads to a modified susceptibility, the so-called Curie-Weiss behavior. And we found that the system is paramagnetic, but only above a certain temperature, the Curie temperature. And when we move below that, we will get magnetic ordering and spontaneous magnetization. And that's what we're going to look at in the first part of the fifth lecture. So let's begin by considering a J as a half state, okay, as we did initially for paramagnetism. Okay, so if we take J being equal to a half, and you recall that we derived that using statistical mechanics, that the magnetization was n mu b hyperbolic tan of alpha, where alpha is mu b over kt. Now we're going to be interested, so let me just label that equation as equation 1. We're going to be interested in the situation with no external field, okay, because we want spontaneous magnetization. So for no external field, B is just equal to the Weiss field. Okay, in other words, B0 is equal to 0. Okay, and this means that alpha is mu naught B Weiss over kt. But we also know that the Weiss field is equal to mu naught, this constant gamma, times the magnetization. So if we take together this equation and this equation, we will get what I'm going to call equation 2, which is that m is equal to Boltzmann constant times temperature over mu b, mu naught, and the constant gamma, all times alpha. So that's my equation 1 and my equation 2. So how we need it must be the case. I've got two separate equations that relate m to alpha. Okay, so how do we solve them? Well, it's a very intuitive way is to think graphically. So here we have some axes. Let's call this m and this alpha. Let me plot in red equation 1. Okay, we're going to get something like this because it's just a tan function. And in blue, I can pop on the so this is our equation 1, and the equation 2, which I will pop on in blue, is a straight line. Okay, this is equation 2. And so the solution of 1 and 2 is this point here. Okay, so that's our value of m and alpha for spontaneous magnetization. Okay, so what I could do is I could read off here, and this would be the value of the spontaneous magnetization. Okay. So this obviously is going to depend on temperature. Okay, so what would change if I looked at different temperatures? Well, this equation here, m as a function of alpha, doesn't depend on temperature. But in the second equation, m as a function of alpha, and here it does. Okay, so the higher the temperature, the steeper the line. Okay, so let's go on. That's just that written out in neat. Let's look at the effect of temperature. So I need to draw set of axes again, try and draw them fairly big. So this is M and this is T. I had my equation 1, which is my hyperbolic tan. It's doing something like this. Okay, and let's pick a few different temperatures. Okay, so we know that we saw there that M is proportional to T times alpha with a bunch of other constants. So if I'm at fairly low temperatures, maybe I've got a line looking something like this. Let's call that T1. And then let's go to a higher temperature. Call that T2. And maybe another temperature. Okay, T3. Oops. Okay, so just to recall that T3 is greater than T2, which is greater than T1. Okay. So the thing that's important here is the value of the spontaneous magnetization. You can see as I increase the temperature, the value is say about here, and then it's a little bit lower, and then it's lower still. And so as I increase the temperature, going from here to here to here, the value of the spontaneous magnetization is getting smaller and smaller. Okay. And there must come a point at which it vanishes, and that is our Curie temperature. We've moved then into a paramagnetic state. Okay, these two equations, equation 1 and equation 2, then have no solution. Okay, again, that's written out a little bit more neatly. Let's look at so let's see if we can get an equation for this Curie temperature. So again, let's just sketch this out. Okay, I'm going to have my equation 1, doing something like this. Okay, so this is my equation 1, where M is equal to N mu B hyperbolic tan of alpha. Now, I want my equation 2 to be just at the limit, the point at which the saturation magnetization disappears. And so if I draw that on like this, okay, this will be when T is equal to theta C, the Curie temperature. Okay, and so that's my equation 2. I had M being equal to Boltzmann constant temperature over mu B, mu naught, constant gamma, all lots of times alpha. Okay. So I want it so that these lines just intersect. So they intersect actually only at the origin here. What that means is the red line must be a tangent to the black line at alpha is 0. So what I need to do is find their gradients and equate them. Now, if you recall that for small alpha, hyperbolic tan of alpha is approximately alpha. So in other words, the gradient, which would be dm by d alpha, the gradient of this at alpha is equal to 0 is equal to 1. Okay, if I differentiate alpha with respect to alpha, I just get 1. Okay, so the for the Curie temperature, theta c, I want the gradient of equation 1 to equal the gradient of 2 at alpha is equal to 0. So we said the gradient of 1, well, the gradient of tan alpha is just 1. So in other words, the gradient of m is n times mu b. So that's n times mu b. and that's going to equal the gradient of equation 2, and that's just kT. Now we're k theta c, sorry, because we're at the Curie temperature, over mu b mu naught gamma. So quickly rearranging for theta c, we have the n mu b squared mu naught gamma over k, that's the Boltzmann constant. Okay, so this is the Curie temperature. And we can see certain things. So if we increase this molecular field constant, so the effect of all the other spins on one particular spin, so that's gamma. If we increase gamma, we increase the Curie temperature. Okay, so that kind of makes some physical sense.